Hey everyone, welcome to another one of our deep dive videos. I'm joined by Erik. We're going to be digging into the circular buffer exercise this week. I thought it'd be good to start off just chatting with Erik about what circular buffers actually are, and also where they're used in the wild. This is actually a real data structure. It's not a toy exercise we've made. And as you'll see in a minute, it's actually quite a fundamental data structure. We're going to be looking at a few different implementations. And really, the underlying topic for today is the differences between the different data structures and the memory allocations that you can use to build this. We're going to be looking at lists, at arrays, at immutable arrays, immutable arrays. We're going to be digging into all of this stuff, understanding about why different things are optimized in different ways, and looking at a few different languages, some functional, starting off with an object-oriented one, and seeing some differences. So Erik, welcome. Hi. Do you want to just start off by just explaining what a circular buffer is? And then in a minute we can actually look at where it might be used.
Absolutely. A circular buffer is a data structure, which means that it is a thing that keeps data in it. So it stores data, multiple items usually, because otherwise it's fairly useless. You're probably more used to having arrays or lists, but you can see a circular buffer as a variant of that. And it has a couple of very specific aspects to it that, for example, lists don't have. Lists are dynamic, so you can add things to it, and it will keep on growing and growing until you've run out of memory. So you can probably put a lot of items in a list before that happens. A circular buffer, though, is limited. So it has a capacity, and the capacity is the maximum number of items that you can store in the list. And that is known at when you create the circular buffer. So you can't change it later on. It's basically you set it once and then it's fixed. And the idea then for the circular buffer is, from a functionality viewpoint, is that it acts like a queue. So you put things in, and when you read something, you get returned the thing that was put in first. So it's a first in, first out queue, FIFO. Or you've probably heard of that before. You also have LIFO, last in, first out, and that's usually what a list is, or a stack, actually. So the stack's probably the best example. So the last thing that you put on the stack is the first thing that you get out when you read. The last thing is the thing that you get out. No, that was slightly confusing. So the circular buffer has a fixed capacity, and when you read things, you get back the thing that you put in the first. So that's the key thing.
We were talking just before we started recording about how actually this is useful as a buffer. And I thought it would just be worth explaining actually to people what a buffer is, because I realize some people might not really be familiar with buffers. And buffers are a data structure, but a sort of a wider concept of something that holds memory for normally a temporary amount of time. So a good example might be if you're streaming a video. You've got data coming in on one side, that is the video being recorded, and you want to be processing that data. So the data starts to flow in, you've got a processor on the other end, and that's pulling it off, processing it, streaming it out to whoever's watching the video. And that buffer sits in the middle, and it's where that data is held while the processing hasn't yet happened, but while more data is coming in. And you could add more processors, more things that can handle the data if you've got lots of video data coming in, or you could have less things that process the data if you've got less data coming in. So buffers tend to sit in any sort of space where you've got data coming in and data needing to be processed. You have things like file buffers where something might be writing to a file, and that might be a temporary space before that file is stored on a hard drive or something else is done with it. And Erik, we were talking about the advantages of, say, circular buffers over just normal buffers. And one of the things you said was about DDoSes, for example. Do you want to explain what a DDoS is and how a circular buffer might help?
Yeah, a DDoS is a distributed denial of service. But the key point about DDoS is like it's an attack where you're trying to get the system that you are attacking to basically crash. So one way in which you can do that is by just flooding it with requests. So maybe you have an API and you have a queue in the background, but you have like a million different machines all adding things to the queue. which means that every single time that API method is called, memory is allocated. So the memory would grow hugely. So at some point, memory will run out and your application might crash, or maybe it will do it gracefully if it's on the beam. But for many languages, that is not the case. So the denial of service for a queue could be just to flood it with requests, to have it be processing a large amount of items. It could also be that it doesn't crash, but that it becomes very slow because there is so much in memory that it has to jump from one point of memory to the others. And we'll get back to that later on. But the point of a circular buffer is that you don't have this unbounded growth because you have this capacity and it will never exceed that. So with the circular buffer, you determine how much memory you want to allocate. And then even if like 1 million people would try to write to the circular buffer, it will never grow beyond the capacity. Which leads us also, by the way, to what does circular actually mean? So suppose we have 7 items in our circular buffer, a capacity of 7. So you keep on writing, but at some point it's full. All the elements in the circular buffer have been allocated. So what do you do when you get another request to write? The default way in which you would do that is to overwrite the first item. So basically you go around if you would draw it out. So you keep on adding new items until you've reached the beginning. Then you start going on from the beginning up until the end again. So you would do like a circle, which is a circular buffer. It's also called a ring buffer, if somebody has heard of that. So that is also more example of that. That's actually like a ring. So it's like a round structure. Although we don't really have round structures in memory. So.
No. So the key things here that make this an interesting, unique thing are the first in, first out properties. So it acts like a buffer. What comes in first gets processed first, and more things can get added, but that it's constrained in size. So eventually it will hit capacity and it will stop, but it has a clever way of dealing with all of this data coming in and having a fixed size, which is to just start again at the beginning and keep moving around in this loop. So, okay, let's look at the first solution here, Erik. The first solution we've got is a C# solution. And you had this down as like a bit of a cheaty solution, and we were going to talk about why it was a cheaty solution. But then as we were just exploring this, we discovered that this really is a cheaty solution because this solution is using a queue, and we can talk a bit more about this in a second. But when we actually went and looked at the C# programming language and looked at how the queue is implemented, we discovered that actually queues are implemented internally as circular buffers. So if you're using a queue in C#, then you are actually using a circular buffer under the hood. So somebody is implementing circular buffer here by using a circular buffer, which is definitely our definition of cheating. But to be fair to them, they probably didn't know that at the time. But yeah, talk us through what this code is, what it's doing, and this is sort of the most simple example that we'll then build on as we move forward.
Yeah, I think you can see that it's cheating just by looking at how many lines of code there are in this example. So it's almost only shelling out to methods inherited from the base class. So we have a constructor with a capacity, which we set. The only reason why we actually need that is to do a check to see if we've hit the capacity, because even though this is maybe slightly interesting to people, the queue is implemented using a circular buffer, but it is actually unbounded. So you can add items to a queue unendlessly until you've reached the ends of your memory. So how would that actually work? And internally, how that will work is when you've reached capacity and you try to write a new item, it will basically create a new circular buffer, couple the old items into the new one, and that new buffer must, of course, have a bigger length, because otherwise you could not write to it. So it will basically keep on using new circular buffers if the limit is reached, but then make them bigger than the previous one so that you have more memory space. And of course, there are clever algorithms on when you need to do that. But you can actually see that.
Can we see that in this?
Yeah. Do you see on line 34 growth factor?
No. Yeah. Okay.
Yeah. And you see minimum grow. And there's
Yeah,
also a shrink
I see.
threshold, which I assume is like the reverse
Yeah. Okay.
when there are less items, when you've removed a lot of items by reading. So
And that's this.
yeah,
You can see here when full, the new capacity is set to the old capacity times the
precisely.
growth
Yeah.
factor. This is a good example of where languages like C#, which are, I mean, most programming languages are open source, but C#, very readable, very well commented, documented language. So it's always fun to understand what's going on underneath the hood, because you can learn tons from this. Okay, so going back to our solution, Erik, we want it to be a fixed length though. So this is we're almost removing that capacity that's been added into the queue on top of the circular buffer in C#,
Exactly.
and removing that here by putting this hard-coded capacity lock on. So
and then
okay,
the only thing that we're doing in read, we're checking if counts equal to null. I assume that this was done because DQ, which is the C# Q variant, maybe throws a different exception, and our test required another exception, because I can't imagine that it wouldn't throw when it was empty. And then for the right is what you just said, that we have to add this additional check to see if we're at capacity, so that we don't actually use that this feature that the queue is boundless. And then we throw an exception. And for overwriting, so we have in this exercise write and overwrite. And write will throw when it is at capacity, so when it is full, but overwrite won't, and it will actually overwrite the first element. And in this case, and this is how many implementations do it, is to read the first element, and we'll just ignore that value, and then we're gonna write to it. So that's a typical trick.
Okay, nice. So that's our C# one. So we're implementing a circular buffer on top of a queue, which is on top of a circular buffer. A bit of a strange one, but it's cool to see. And it's also cool that we didn't know this was the case until about 5 minutes before we started recording this. So yeah, nice bit of serendipity for us there. So moving forward onto the next one is this solution we have here in Python. And we can ignore these first couple of just exceptions that are defined at the top. But I guess the key to this, Erik, is this line 25.
Yeah.
And this is a good opportunity for you to explain to us what these square brackets are in Python, and what that means in terms of this solution.
Yeah, so square brackets are, they create a list. In this case, it's the empty list, so no items are in the list. And a list is different from an array. If you are uncomfortable with what an array actually is, an array is a data structure that has a fixed amount of memory, like a circular buffer. But an array is just contiguous bits of memory. So when you have an array of, 5 integers, if you would look at in memory, you would find that those integers are next to each other. And that will be a key thing that we will go into more detail later on. But that's one of the absolute brilliant things about arrays, is that the items in the array are next to each other in memory. Whether or not those items then refer to other bits in memory is another thing. But if we're just talking about integers, etc., there will just be a couple of integers next to each other in memory. And the array, the downside is that an array can't grow. So if you want to, if we've reached that limit, like with the circular buffer, you want to add something, you have to do the same thing that the C# people did. You have to create a new array and then copy the memory. That is, in some cases, fine. In some cases, it isn't, which is why you have other data structures too that work slightly differently. A great example are lists. And lists are usually, so when you create an element, you allocate only that element in memory. So you won't allocate upfront all the items that you think you're going to allocate. You just allocate that one thing that you are adding. And then when you add a new element, a new thing is created in memory. But it could be on, a completely different place in memory. It likely will not be next to the previous allocated element. And that is very important for performance. But let's hold off on that for a little bit, and just note that here in Python, the buffer is a list, and you don't see anything being done with the capacity. So that is already an indication that we don't have a fixed amount of memory being allocated. And then when we look at the actual code, for example, in the write function on line 36, you see self.buffer.append data. And that is the point where you try to add a new item to the list, which means that a new element is created in memory. It's a node in the list usually. The terminology varies between languages, but you just have to read this as a new bit of memory is allocated, and we make sure that the list knows where it is. And then maybe internally it will update state so that it knows where to go to the item, etc. But the idea is new memory is being allocated. Sorry.
No, go.
Yeah. So if we look at read and on line 32, so what does reading of a list mean? Well, in this case, it says pop, which is stack terminology for remove the last item. But this is pop 0. So that's actually a little bit weird because you're popping the first item, which is like almost the inverse of pop. So I'm not entirely sure about the economics of that function call. But one of the benefits of a list is that you adding those items to the end of the list is very fast, but it is usually also quite fast to remove for example, the first item in the list. So you can see elements in the list, and is often implemented like a linked list, which means that when you have an element for the number 1 in memory, and you have an element for the number 2, so the way that the list keeps track of those is to have the number 1 have a pointer, so like a link to the next element. So then if you have the list knows the first element, and then it can just walk all the nodes. So it will start by going to the first node, and then we'll see, hey, this first node has a pointer to the next element, which is the second is the element with 2, and then so on until there is a node that doesn't have another element in it. So to get to the end of the list, when you have, well, it depends on the implementation of the list. But a simple list would require you to walk the entire chain of elements. But of course, for the first element, this isn't the case because that will always be where you start. So it's easy to get there. So it's fast. But if you have to do something with the last element of a list, and the list is implemented as I've just said, then it becomes very expensive.
Cool. That makes a lot of sense. So this, again, pretty straightforward implementation. Again, you can sort of feel it's maybe a little bit cheaty just by the sort of, again, the lack of doing much that's that's not already in there as code. What do we normally call this pop 0? I know in Ruby it's called shift instead of pop. Is there a term that other languages tend to use for that?
Yeah, shift and unshift are quite common to use to do things with the first element. So yeah, but I rarely see pop.
Okay, so yeah, I've not seen that before. So next up, we're looking at Elm. And Elm is a functional language, and so this is using an array, but functional languages tend to use immutable data structures, Erik. So this is all a little bit different to what we might think of when we're looking in Python or something. So do you want to tell us a little bit about the immutable data structures, what Elm is actually doing under the hood, and then we'll look at the code itself?
Yeah, so I haven't actually entirely found the source code of these Elm bits, so I can't go into detail, but I can say what in general holds is that Elm, of course, also has lists. So lists are probably, when you are using a functional language, the default thing that you are using are lists. And there are very good reasons for that, but we don't need to go into that. But there was clearly an effort being made to use an array here. And that is for because that is what actually a circular buffer should use. So this is already an implementation that actually does the work on allocating an array. The thing that is slightly weird is when you get to line 11. So you have a function on line 10, define new, so create a new circular buffer. of the specified size. But you can see it's using array.empty. So it's not actually allocating the array with, I don't know, the size number of elements in it. So the array is an immutable data structure. And an immutable data structure means that you can't change anything inside the data structure. If you want to add something to it, you get a new version of the data structure. So you might be thinking this is absolutely horrendous because this is very wasteful. So maybe I have a list of 100,000 elements and I want to add another element to it. Do I then have to create an entire copy with those previous 100,000 elements? Well, it depends on the implementation, but usually the answer is no, you don't. So one of the things about being immutable means that you are guaranteed that that memory will never change. So what if you add that 100,000 plus one element, you would create like a virtual array, a new array that has just a single element, and it says that, hey, for the first elements, just look at that memory there. So it's just pointing to the data that you already had, because it can do that, because it can guarantee that that data will never change because it is immutable. So you have you don't need to copy all of those items. You just need to include a reference to the thing that it was using to append to. So that is how you could implement immutable data structures very efficiently. That's not to say that all languages do it like that, but it is a very common way in which to optimize this. Now, as to what Elm does, I'm sort of like speculating almost here. I assume that at some point, it being named an array, it will actually allocate an array. So, but that's fine, because even that array, it can, under the hood, it can write to it. But the data structure that you get back it's immutable. But under the hood, it can actually write to a mutable array, and that doesn't matter. And that's actually quite a common theme in functional programming in general. You can have a functional shell, and for the things that you don't see, for the implementation, you can actually do mutation. In this case, it might actually be similar to what the C# circular buffer implementation did. So when the array's capacity is reached, it will allocate a new array, but it could also just allocate a new array for just the new data, and then have like this whole immutable reference to the old and the new version thingy. I can't go into detail because I'm not that familiar with the Elm source code. But the key part is that Elm offers you an immutable data structure, even though under the hood there will be mutation. So Elm does it for you. And you can actually see that if you go maybe go down a little bit to line 31 and 32. You can see you have array.push element to the buffer. So we're adding an element to the buffer, and that gives you back a new array. So it's not the same array, although it might be under the hood plus a little extra. And then that is piped into circular buffer with the same size. And that means you're creating a new instance of circular buffer. So that is what it means when you work with immutable data types. So circular buffer itself is also immutable. You can't just change the array within the circular buffer. You have to create a new circular buffer whenever you do mutation. So any of these functions, from clear to push to read, they will always return a new version of a circular buffer instance, even though under the hood it will do clever stuff to prevent this from spiraling out of control.
Very cool. Really interesting.
Yeah, and one last thing that I would like to point out is that the read function, it returns a maybe type. So in the C# version, and the write does the same thing. So whatever you like to show. And that's a functional way of handling errors. So in the C# version, and probably the Python version too, exceptions were thrown. So, but you can't see that in the type signature. So you don't know when it's throwing an exception. But in a functional language, probably there are languages that have exceptions, but most of them tend to not have exceptions, but instead have a specific type that is encoding the fact that whether or not something was successful or not. And in this case, it's called maybe. So it's a very appropriate name. So maybe this went well, maybe it didn't. So and that is what's being done here. So if it couldn't find like a single value, so it was empty, then you don't get back a circular buffer. You just get back, in this case, the element itself, an element of the type. So I'm not entirely sure about that API, but maybe that's what you want. But you could imagine it also being like a specific error string or an error type, probably in a functional language. But it's not. It's different from like object-oriented languages that throw exceptions.
Okay, cool. So that's edgerunner Mert solution in Elm. Next up, we have Crystal. And this you sort of felt was the first like really proper solution to this, Erik.
I even think this is like the prototypical implementation of a circular buffer. If you would go back to the C# source code, you would even see the same names, I think, head and tail. So you don't need to go to that. But if you look up Wikipedia and you check circular buffer, and there's like a pseudo algorithm there with pseudocode, you'll find that the algorithm that they use is this. So this is proper. So on line 7, we see it's creating a new array with the specified capacity. So and this is the only time when we will allocate something array-wise. So when we won't append things or whatever, the only thing that we will do is read and write from this array. So this is the absolute key part of the circular buffer and of this solution. So this buffer array has capacity items. They're initially set to 0, which is fine. Whatever, you don't even really need that unless you maybe want to do something to see if it was already written to, but it's probably just that the Crystal language requires that. So on line 8, you see three fields being set to 0. You have count, which is like how many items have been written to, which is not the capacity. Initially, we don't have any items written to it. And then we have head and tail. And these are the important things. So these are the index for head, where you will be writing to, and for tail, where you will be reading from. So initially, if you visualize this in your head and you have a buffer of 5 elements, the head and the tail will start at index 0. So they have the value 0. So they point to the first item in that buffer. Now, if you write one item to it, the read index will stay the same because that will be the oldest item. But the write index will move one step to the side. So we'll move to the element at index 1. Then if you write again, the write index will move to element index 2. But the read index will stay at that first position because that is the oldest one. You can, of course, guess when you start reading, you read the value from that index, and then you shift the read index right. So suppose we had 3 items written to it. So the write index would be on the 4th. So the next one you write to is the 4th index. The read index was at 0. That was the first element. You get that element and you move it to index 1. So that's the second element. So then if you next time you read it, you get back the second element, and so on and so on. And that is what's being implemented here. Yeah. So you can see on
modulo is the loop, isn't it?
Yeah. So on line 13, so we're doing a read. We're getting the value that is at the index at tail. So that was like where we started out with 0. And then you increment the tail because you're moving to the next oldest element. That percentage capacity is modulo to, that's basically to circle around the buffer. So suppose you were at the last index of the array, then you would have to move back to the 0th element, and that's what that percentage does. So that's modular logic, but it basically ensures that you don't exceed the limits of the indexes. So you circle around, basically. Of course, the count is decremented because you've just read something. But one very interesting thing to note is that we don't actually clear any memory or anything like that. We just leave it in memory. So it's actually still there. We just set the pointers to the different thing. And that is also, it's an advantage because of course, it takes a little bit of time to clear up memory, but you don't need to do that because you're guaranteed through those, if you keep proper track of the head and the tail, it doesn't matter. You can leave it in memory anyways because it won't be written. And then for writing, it's a similar story, but then you're using that other pointer, so the head pointer. So on line 25, you see that you're writing in the buffer in the position of the head pointer. So that's the right index, that specific value. So this could be overwriting a value that was already there. We don't know. And then we do the same +1 modulo trick to move it to the next element. And if we are at the end of the list, we circle back again to the beginning. And the only the little trick is the count equals capacity. That means that if you were already at the, if it was already full, the overwrite, it will be overwriting the oldest value. So that at tail equals head means that the oldest value is then updated to the right index, basically. But it's just a little trick. And that only happens when the buffer was completely full. And in that case, of course, you don't have to increment the count because the count stays the same. You're just replacing values. But if it wasn't at capacity, you increment the count by 1. And then that's it. And then on line 35, you can see there's a clear function. And that makes it very clear, pun intended, that it's easy to clear a circular buffer. You set the count and the head and the tail index to 0, and that's it. The data will all still be in memory, but the user won't be able to get to it because, well, in this case, an exception will be raised. Yeah.
So I think this is a good example of the advantages of having this fixed capacity array. The fact that we don't need to clear, like to sort of, pop 0 effectively or unshift. We don't need to take that value away because we're not freeing up memory because the memory is allocated. So we've already allocated this memory. We've said we need this much memory reserved for this array. So there's absolutely no value in changing what's in that bit of memory to get rid of it. It gives you no performance benefits at all.
And maybe now that we are talking about performance, this is a good moment to start talking about why it is so important to have that array, the elements being next to each other in memory. And for that, we need to do a little bit of a lower level, go into a bit of lower level stuff with how your CPU works. So when you have an array in memory and where you have anything in memory, basically, you're reading from memory. So you're asking the CPU to read something for you. So there's an instruction, read memory at offset, whatever. And then what the CPU will do is it actually won't just read that single bit of memory. It will read more because the CPU will assume that, hey, you want to read this bit of memory. You might actually want to read the thing that is next to it. And in an array, that is quite likely. So what the CPU will do is instead of reading just a single thingy, it will read what's called a cache line. So it's usually 64 bytes. So 64 bytes would be 16 32-bit integers. But the key part is that it won't just read a single thingy. It will read that thing and some more. So the things around it. Now, if you have, and then the next time you try to read, for example, the element next to it, so the next item in the array, it will see, hey, do I have in my cache somewhere in the range where this location fits? So if it is the next element, it will be already in the cache. And the key part about that cache is that it is very, 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 very fast. So you want to get those cache hits. That's what it's called. So when the CPU finds something in the cache, it's called a cache hit. And that basically means you get data back very, very quickly. Memory is fast, disks are slow, but CPU caches are the fastest, basically. You basically can't get faster than that. There are also level 1, 2, and 3 caches. So level 1 being the smallest, but also the fastest. Level 2 being a little bit bigger, but a little bit slower. But if it isn't in any of the caches, then it will have to do that whole bit again, where it tries to look at the memory, and it will read that bit of memory along with data around it. And this is called data locality or spatial locality. And the idea being that things that are in memory that are next to each other are likely to be used often at the same, or at least sequentially. So when you do your prototypical for loop in an array, that will be quite fast because it will use those cache lines. Of course, at some point it will find data that is not in a cache line, and then it will read new data. But you will get the benefits of every single read that you read from a cache line, from the cache of the CPU, because that is so fast. So when you see people trying to optimize code, they will absolutely be trying to use this fact to get as much cache hits as they can.
Very cool. That's a great explanation. Thanks, Erik. And talking of lower level code, I guess that brings us on to the next one of these, which is in C++. And this is quite similar to the Crystal one, is it, Erik?
Yeah, it's similar. It's basically a variation of the theme. It's doing everything that the previous solution did. The only thing that you won't see here is the tail pointer. So like the one that you read from, and that is actually calculated. So if we see you only have an m_first pointer. So that's the I think that might actually be the tail. That is the tail. And then you have a length, so m_length, and that's the number of elements that have been written to it. And you can combine these two. So if you look at the right, you can see that it is m_first plus m_count modulo the length. So it was m_count, not m_length. And m_count is the number of elements that have been written to it. And then you get back the position where you are writing. So you're basically calculating that tail value. Which of course is nice. It also has a downside that you have to calculate it each time that you are writing, which is probably why people usually have it as a specific separate field. But it's valid. So it's just a variation on the theme, and it goes to show that you don't necessarily need that tail because you can calculate it. Head in this case. Sorry, I said tail. I meant head.
Everything else here looks very, very similar to what we've just seen. Okay, cool. Nice to see some quite readable C++. Again, often the case. Once you are familiar with what code is doing, as you move into lower level languages like C++, C, or even as we've seen in previous videos in assembly, it's actually very readable. Often the first thing that's confusing when you're looking at lower level code is just trying to work out what it does. But if you already know what it does, just seeing the actual code itself, totally readable. Okay, and then the final solution, Erik, and this is quite different from what we've seen so far. And this is in Erlang, so this is functional. Talk us through this, Erik.
Yeah, Erlang is a functional language, so like Elm, it has immutable data structures. But the fun thing about this implementation is, and that's the way that this Erlang exercise is structured, and also in Elixir, is that the data structure is a process. So if you've never heard of Erlang or Elixir or anything about the Beam, which is the virtual machine on which Erlang code runs, it is incredibly efficient when running multiple processes. And these are not threads. These are specific things that the Beam supports. And processes are these things that have their own local state, but nobody can get at them. The only way that you can interact with processes is by sending messages to them. And you would never do this in like an object-oriented language. Like we've never seen this in any of the other solutions before here too. But in Erlang, so there is very little downside to creating this process because it is such a lightweight thing, and you get a lot of benefits from it. On line 11, you see gen_server : start link, and that is the thing that starts that process. So the question mark modules means start a process with this module as the code behind it, and then the size is the parameter that we pass into it. I'm not entirely sure about the third parameter, but it's probably arguments. So on the left side, we see curly braces OK, comma PID. PID stands for process ID, and that's what we return to the user. So when you call create and then you pass in the size, you get back the unique identifier of that process. So a process will be started, and a whole bunch of goodness comes with that without going into too much detail. Then you see read, write, size, write attempt, which are the next functions. Those will all get a process ID. And then under the hood, you say genserver :call. And this is message sending. So we're saying on line 14, genserver call, and then we're sending to the process ID that we pass in, and then the Atom read. So that's the message. We're sending a read message. So where is that processed? Well, if you look at line 24, you see handle. And handle means a message came in. You can now look into the contents of the message and then decide what to do with it. And this is using pattern matching. So if the first argument of handle is equal to the read atom, which it would be in our previous case, then we're going to match this if the second argument has this structure. Well, in this case, what it's doing is it's trying to deconstruct the buffer. And to see what the buffer is, we have to go up a little bit. So because the buffer is basically, we see it in line 22. So in it, if you see, you have OK, which is, of course, indicating that everything went fine. And then you see between curly braces, size, comma, and then the empty list. So that little bit, that is our actual circular buffer contents. So this is like the state of our module. So it will have two values.
And this is called... Is this what's responded to up here?
Yeah.
And the start link is
genserver start link will automatically call init. So that's the order. So you have to start with start link, and then because we set :module, we'll look for the init function in this module with we'll pass in the size as the parameter, as the argument. The data structure itself is just very simple. It's just size and initially an empty list, but a list. So on line 24, we're trying to read from a buffer where we're ignoring the first. So that's the size. So we say underscore. We don't care for the value. It matches any value. But if the second value, the list, is empty, then we're trying to read from an empty list. And then we're replying. So you see reply. This is all messaging terminology. And what we are replying with is error empty. And then buffer is, I think, the context, or I'm not entirely sure, but it's sending an error message that this is an empty buffer. So, but this is all messaging. So we don't have exceptions being thrown or whatever. This is all messaging. So the consumer, the one that sends the message, will get back this, and then it can verify and then handle that and do pattern matching on the consumer side too. So the consumer won't ever get to the internals. And then the same thing we can do for the rest. So if we have a regular size, so we're not doing anything with patterning, we're just giving the things names. So then we reply with list : last. So that's the oldest. I think it's pre-pending to the list. So that's the last item in the list.
Okay, so it's almost a reverse to what we've seen everywhere else.
It is, yeah.
Okay.
Yeah. And that depends on the implementation. That might not actually be very efficient because of that reason why you have to, when you read things from the list, you start out with the head and then you have to, there are lists that also allow you to do the reverse starting from the last one. So maybe it's doing that. And then it says the new state. So that's on line 28. So this is all very immutable. So if you remember the Elm thing, where we keep on creating new circular buffers, we're doing something similar here. We're creating new state. And of course, the size stays the same, but the list is different because we've read something. And list drop last is probably obvious what it does. So it will get everything from that items but the last item. And then, the other functions are basically variants. Maybe the interesting to see is that on line 35, writing an item to the list means prepending it. One line above.
Mm-hmm. Sorry.
Yeah. So
yeah.
Yeah. So you see item pipe sign items. So that means that the last written item is piped in front of the list, and that's why that's also a very common functional pattern. When you add things to a list, you add them to the beginning, because that's most efficient, because then the list just needs to add, you don't have to walk through that entire list. And then the rest is just pattern matching to make sure that you're only calling things when you're doing the right thing. But it's fun and very unconventional for other languages that are not used to having these processes being so flexible and so lightweight. I would never think of doing this in a language like a C# or an F#. I wouldn't start a process to have a data structure, but in Erlang you absolutely can. Nice. It totally makes sense too.
Nice. You can also see a bit of guarding here on the pattern matching.
Yeah. And order is
this syntax, if you're so this syntax, if it doesn't feel familiar, I recommend watching our recursion video that we did a couple of weeks ago, which does look at this syntax and how the concepts of having a head and a tail, where the tail is a list of items, or I'm being very careful with the word list at this stage, and the head is a single item, and you can construct them together like this. So if you haven't seen that video, definitely go and check that out. But yeah, it's so conceptually strange, Erik, to use processes for this. But I guess that's just the way it is. Very, very, very distributed in terms of how we think of it. And can these processes run on different systems as well, or is it locked into the one? Yeah, I think they can as well.
Just to be sure, this is not a proper circular buffer, of course, because it's allocating new lists. This isn't pre-allocating data, but it's still very cool.
But fascinating to see, nevertheless. Yeah. Cool. Okay, that's the last of our solutions. I hope that was an interesting tour for you. I feel like it's been a really nice refresher for me on all of these different data structures, and I've never seen this a solution that uses processes like this before. So that's really cool to see as well. Thanks so much, Erik, for all of your insights into this. Thank you, everyone, for watching. Please leave a comment. Tell us what you think of these solutions. If you've got a nice solution of your own you've done, please link to that as well. And always appreciate if you can give the video a like as well. That really helps out the channel. Enjoy solving the exercise. Try it out in some different languages, and look forward to seeing you in a future video. Bye for now.